Hello Year 10, Mrs Allbone here. Welcome to your second lesson for week 5. Today you can see on your screen we are looking at velocity time graphs, and you have the key facts listed for the information that we are going to cover in this lesson. As always, I would like you to pause the video and have a go at these starter questions. Here are my answers. Again, pause the video and just check that you agree with my answers before moving on. Okay, so today we are looking at velocity time graphs. Now, what does a velocity time graph tell us? Well, it's very straightforward. It simply tells us the speed of an object during each unit of time as an object is moving. Now, after 5 seconds, the object has moved. The object is moving at a velocity of 10 meters per second, and after 10 seconds, the object is moving with a speed or a velocity of 20 meters per second, and you can quite clearly see that from that graph. Now, one of the other key facts that you need to understand from this lesson is talking about acceleration. So what do we mean by acceleration? Well, quite simply, acceleration is defined as the rate of change of velocity, the rate at which velocity might change. And one of your key facts is the equation that's associated with acceleration. So you look at your change in velocity, divide that by the time taken, and that will give you the acceleration of the object. And those two things are very important for you to take away from this lesson. So if we go back to our velocity time graph, what I want you to do is just take a quick screenshot of this graph and then use it to answer these questions. Okay, so after 5 seconds, the object is moving with a speed of 10 meters per second. So the acceleration after 5 seconds, well, the object went from 0 to 10 meters per second. So the change in velocity is going to be 10 meters per second, and that happened in 5 seconds. So your acceleration is 2 meters per second squared. After 10 seconds, the object is moving with a velocity of 20 meters per second. So the change in velocity is actually 20 meters per second because it started from 0. That happens in 10 seconds. So again, the acceleration is 2 meters per second squared. So what does the straight line tell us? Well, it's telling us the value of that acceleration. So the gradient is telling us the acceleration, and you can see that it's accelerating at the same rate. So a straight diagonal line like this tells us that the object is moving with a constant acceleration, and in our case it's moving at 2 meters per second squared. But what do we actually mean by 2 meters per second squared? Let's see if we can break that down a little bit further. So all that means is that every second the velocity is increasing by 2 meters per second. So there is an increase of 2 meters per second, and that's how you get this little squared value up here. So if I just add some values here, after 1 second the velocity is 2 meters per second, after 2 seconds the velocity is 4 meters per second, after 3 it's 6, after 4 it's 8, and then 5 we know it's 10. So every second you can see the velocity has increased by 2 meters per second, and that's what we mean by the acceleration. Okay, so when we have a straight line along a velocity time graph, what does that tell us? Well, it means the object is moving at a constant velocity. It doesn't matter how much time passes, the velocity is constant at 10 meters per second. So the object is moving at a constant velocity. Okay, I would like you to pause the video now and just have a go at working out the acceleration of these three objects. We know a straight line like that means these objects are moving with a constant acceleration. So pause the video and just work out what the acceleration is for each of those objects. You should find that object A is moving with an acceleration of 2 meters per second squared. Object B is accelerating at 1 meter per second squared, and object C is moving at 0.5 meters per second squared. So we know the gradient on a velocity time graph represents the acceleration, and this is also showing you that the steeper the gradient, the higher the acceleration. So you can see A is accelerating much more quickly and the gradient is much steeper when compared with C, which is still accelerating, but it's not accelerating as quickly. So we know the steeper the gradient, the higher the rate of acceleration. Okay, let's just return to our straight line. Now we know that a straight line tells us the object is moving at a constant velocity. From this graph we can see the vehicle is travelling at a constant velocity of 10 meters per second, and it does that for 15 seconds. Now you know from our previous lessons that distance travelled is equal to velocity times time, or speed times time. So I would like you to pause the video for a moment and just use that information to work out the distance travelled. Okay, so distance travelled is equal to velocity times time. So the velocity is 10 meters per second times 15 seconds, and that gives you a distance travelled of 150 meters. Now how could we use our graph here to work out the distance travelled? Well, quite simply, year 10, it's this area under the line. This area represents the distance travelled. Well, how? Because when we did our calculation, we multiplied 10 meters per second by 15 seconds, and that gave us a distance of 150 meters. And that's exactly what we would do if we were working out the area under this graph. So this distance, or this length, would be 10, and this length would be 15, giving us a value of 150, in this case, meters. So the area under the line on a velocity time graph represents the distance travelled. Now I have an example here for you. This object is obviously accelerating with a constant acceleration and then travelling at a constant speed. So I would like you to pause the video and use this graph to work out the total distance that the object has travelled. Okay, so the easiest way of doing this is to break the area up into two separate parts. So we have this area here, which would be 4 times 8, that distance of 8, which is 32, and we half it because we're looking at a triangle, and that gives a distance travelled of 16 meters. And then for the journey, or part of the journey where the object travelled at a constant speed, we have a distance of 48 meters, which you get by multiplying 6 by 8, and that gives 48 meters. In total, we add those two together, 16 plus 48, you should have got a value of 64 meters, which is the total distance travelled by that object. Okay, so far we know that a diagonal line like that shows that the object is constantly accelerating. The more steep the gradient, the faster the acceleration. We also know here that the object is moving at a constant velocity when we have a straight line. So what does this section of the velocity time graph show us? Well, that's quite straightforward. Here the object is constantly decelerating. So again, here this is our acceleration, and this means the object is slowing down, and that's what we mean by a deceleration or a negative acceleration. It means the object slows down. I've got another small task for you to do, year 10. I would like you to look at the motion of this vehicle moving here and then here, and I would like you to describe the motion of that vehicle and its distance covered. Quite similarly, if we look at the yellow section first, here the object is moving at a constant speed of 20 meters per second, and it did that for 10 seconds. So if we look at the area under the graph, we will see that that is 20 times 10, so the distance covered was 200 meters. In this section, the object is decelerating or slowing down, and if we look at the area here, then we need to say 20 multiplied by 5, that the difference there is 5, and we need to take half of it because we are wanting the area of the triangle, and that gives you a distance of 50 meters. So in total the distance covered was 250 meters. Now if you feel you need a little more practice, I have another graph here. So take a look at that graph, maybe take a screenshot of it and use it to answer these questions. So you should find that this is fairly straightforward, describing the car journey. Well, we have a constant acceleration, then the object travels at a constant speed or constant velocity. We have a further acceleration, and then the object travels at a constant speed again, and then it decelerates back down to 0. The car accelerated twice, so you should have a value of 1.5 meters per second squared here and 1 meter per second squared here. Between 8 and 12 seconds the car travelled at 7 meters per second, and the deceleration of the car you should have got as 1.16 meters per second squared, because it went from 7 down to 0, and because it was decelerating we can describe that as a negative acceleration or simply use the positive value because we are describing it here as a deceleration. The total distance covered by the car is this area underneath the graph and underneath the line, and you should have got a total area of 78 meters. So if you haven't quite got that, just pause the video and see where we've got that from. Now, as part of your facts, you need to know the equation for acceleration, and we can put that in a triangle in exactly the same way that we do our other equations. Now we know what acceleration is. It's change in velocity divided by time. So when you cover acceleration up in the triangle, you have got to be left with change in velocity divided by time. The only way to do that is to put change in velocity up here and time down here so that it fits. So when we put a triangle together, it should look like this, and again, if you know 2 of the values, you will always be able to work out the third. But you have a second version of that equation in your facts, and that's because of this part here, the change in velocity. Now, change in velocity is actually described as your final velocity minus your initial velocity. So when you think of the examples we've looked at so far, year 10, if a car accelerates from 0 to 20 meters per second, then its final velocity is 20 meters per second, its initial velocity is 0. So we've just ignored it. But Sometimes that's not the case, and that's what we're going to look at now. So it's important to know your final velocity and your initial or starting velocity, and then we can put that into the equation in exactly the same way. So here our change in velocity is described there, and that would go at the top of the triangle as well. You also need to be familiar with some of these symbols, year 10. So A is acceleration, V is equal to final velocity, and U is equal to initial velocity, and T is time. Very often you will see the equation written like this: acceleration, final velocity, initial velocity, and time. So if we look at this example here, we've got two objects, X and Y, two cars, and we're looking at the velocity time graph for each of those. Now if you're asked to calculate the acceleration for both cars up to 6 seconds, so 6 seconds is here, where we've got a constant acceleration for both of them. So if we use this abbreviated version, you can see for car X, its final velocity is 15, its initial velocity was 0, so the difference is going to be 15, and that took part in 6 seconds. So it had an acceleration of 2.5 meters per second squared. Car Y, on the other hand, I've estimated that to be about 18 meters per second, its final velocity. Again, its initial velocity was 0, so 18 minus 0 is 18, divided by 6, and that gives us 3 meters per second squared. So if you look at car X, just finishing off this example, after 10 seconds it had travelled up to 25 meters per second, so the change in velocity was 25 minus 0, and that was all in 10 seconds, so it remained at 2.5 meters per second squared. Just reiterating again that it's telling us that we are moving, this object is moving at a constant acceleration. Okay, I would like you to use this abbreviation to try and answer this worked example. So pause the video and just have a go at working this question out. Okay, so using our equation here, we should find that we are looking for acceleration. We know our final velocity is 18 meters per second, and we know our initial velocity is 2 meters per second, and we know that acceleration took place in 4 seconds. So it's quite easy to put those values into our equation. Final velocity minus initial velocity divided by 4. It's very important, year 10, that you do this calculation first, which is why I have put brackets around it here. So 18 minus 2 is 16, divided by 4 gives us an acceleration of 4 meters per second squared. Okay, taking that forward, I would like you to pause the video and just have a go at answering these questions. Okay, so the movement of our object, well, we know it's a straight line and it is accelerating. So here the object is moving with a constant acceleration, started off at 4 meters per second, ended up at 12 meters per second, and that all took place in 10 seconds. So if you calculate the acceleration of this object, you should find you get a value of 0.8 meters per second squared. Final velocity was 12, initial velocity was 4, so the difference is 8 meters per second divided by 10 seconds, which gives you 0.8 meters per second squared. If you calculate the distance travelled by the object, then you should have worked out a value of 80 meters, because when you're looking at the distance travelled, you need to consider the whole of the area under the graph or under the line. And that's really important, and it's often something that students get muddled with, that they only work out this area underneath the bit where they are accelerating, but you need to work out the area of that total area under the line. So remember that if the graph doesn't start at 0 meters per second, you calculate the acceleration using this gradient here, but you have to calculate the distance travelled by using that whole area. Okay, so that's about it for our lesson today, Year 10. It's really important, the two things we've looked at, distance time graphs and velocity time graphs this week, they are very, very similar, but they mean very different things. And the only way to become comfortable with that is to practice. So what I would like you to do just for a moment is pause the video and think about what A, B and C mean for each of these different types of graph. Okay, so here you can see that the difference between these two graphs. Here we are moving at a constant velocity away from your starting point. Here the object is stationary, and now the object is returning to the starting point with a constant velocity. Here the object is accelerating with a constant acceleration, moving with a constant velocity, and now moving with a constant deceleration. In addition, here, if you look at the area under the velocity time graph line, you can work out the distance travelled. That is not the case with a distance time graph. Okay, I would like you to look at this past question to finish off with Year 10. So pause the video and have a go at this part of the question, and then pause the video and have a go at this part of the question, and then finally mark your work with the mark scheme. Okay, so that ends the lesson Year 10 on velocity time graphs. You can see we've covered what a velocity time graph is. The horizontal line means the object is travelling at a constant speed, and if you've got a sloping line, then it means the object is accelerating or decelerating, and the gradient will give you the magnitude of that acceleration. We've looked at the two versions of the equation for acceleration, and we have also explored the fact that the area under a velocity time graph is equal to distance travelled. So that's the end of the lesson, Year 10. I hope you have found that useful. As always, email me if you've got any problems with it and we can talk about them. But other than that, have a good day.